Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com. And today we're going to be looking at the product rule and the quotient rule. If you like this video, feel free to click the like button. You can comment in the comments section. You can also share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comments section of the intro video, including this one. Let's take a look at the key ideas from today's worksheet. First, we should work neatly, especially for longer calculations. That's true in calculus, and it's true in all subjects of mathematics. We also want to use an implication symbol to organize our work where needed. It's a common blunder to misconstrue this symbol with a common equal symbol, but the equal symbol is put in between two expressions that have the same value. This symbol is put in between statements when one statement implies another, and it's a great way to organize our work. Let's take a look at the formulas that are provided for this worksheet. We have some familiar ones, the power rule, the rule to differentiate a constant, how we can pull constants outside in front of a derivative, and also how we can distribute derivatives across sums and differences. These last two, 3 and 4 together are called the linear properties of the derivative. We have the rule to differentiate an exponential function, base e. We have higher order derivative notation, both using the primes and the Leibniz notation. And then we have the new guys on the block, the product rule and the quotient rule. So these rules are slightly higher level, and they can be derived, if you're interested, by using the limit definition and making use of what's called zero-sum steps. Zero-sum steps are steps that appear often in mathematical proofs where a mathematician will add and subtract the same quantity to an expression to gain some advantage in its representation. It's like somebody offers you $5, but before you can put it in your pocket, they collect the debt of $5 that you got. So it's like, what just happened? I got 5 and I lost 5. That's a zero-sum step. Here, we're not going to be proving these product and quotient rules today. Instead, we're going to be applying them. Let's take a look at some problems. Let's try this first problem. It reads, for the following, you need not simplify, find f prime. And f is given as a product of two binomial expressions. Of course, we could multiply out these binomials using the FOIL technique, and then we could differentiate the resulting polynomial using things like the power rule or the linear properties. But in the spirit of this worksheet on product rule and quotient rule, we're going to use the product rule as it's given above. So according to the above statement, the derivative of a product of two functions is a sum of terms. You have to alternate between differentiating the latter and the former functions and multiplying by the other. So here we have it, the derivative of f times g. It's g prime times f plus f prime times g. You could easily permute these terms. There's nothing wrong with that. Writing this as f prime g plus g prime f, as I often do in my own work when differentiating using this rule. So we need to label the functions as such. Maybe because f is already taken, we shouldn't use f. So we'll use maybe u and v as it's stated. So that could be u, for instance. Why don't we label this first factor as u and this second factor as v? Now it's a direct application of the rule provided on the tail end. So we have, that implies that f prime of x is equal to, I'm going to do u prime, which is 2 times 3, so that's 6x squared plus 9, multiplied by v as it is. So I've knocked out what is this term right there, and we're going to add what is v prime times u. So that will be 4 multiplied by u as it is. So that's 2x cubed plus 9x. And with that, we've knocked out this term and we are done. Okay, so we've worked out the derivative of that function f by the product rule. Note the use of the implication symbol to separate our statements, and using proper notation, it would have been a bit of a blunder to label any one of those factors, u or v, as f, because f is already taken. So even though the product rule was stated where the two factors are f and g, you can't use f and g really here, because it's always an issue in mathematics where you have f representing two different functions. Let's try the next one. So we'll use here the color blue for that one. We're going to relabel the functions so we can, like clear u and v. It's like they're now completely clear of definition. This will be my new u, and this will be my new v. So that means that f prime of x, I suppose we got to clear f too. So f prime of x is going to be u prime. So that's going to be a 3x squared plus 7 times 2, or 14x, and minus 2. This will be multiplied by v as it is. So we just cut and paste. And now we need to perform addition, adding v prime u. So v prime u works out in this case to be 3 times 7, which is 21x to the power 6 plus 8x. Well, the derivative of that one is just an 8. There we go. That's plus v prime times u. So got to be super meticulous when applying these rules. So simple to make a typo, a copy error that will then propagate through your work, giving you a faulty answer. I believe this is looking okay. We can always do a check here. So this is supposed to be u prime. It's looking pretty good. Times v, that looks right, plus v prime. I believe that's looking good. And times u. All looks well. And with that, we have applied the product rule. Let's try some other problems. In this next one, we're asked to first find dy dx, and then evaluate it at x is equal to 1. Because f and g are no longer taken, we can go ahead and dub this f and this g. Why not? So we're going to be using the version of the product rule stated initially in the rule above. So I usually permute the terms. Since there is here no penalty for doing this, I'll write f prime times g term first. Even though it appears as the latter term in the rule, there is nothing wrong with this. So we have dy dx is equal to, we can write out the rule if we want. So there's nothing wrong with taking an extra step, right? So there we go. And f prime, very meticulously will differentiate, putting the result in parentheses. The derivative of 9x is just 9, right? Whenever you differentiate a linear function, you just get the slope. So what about the derivative of minus 2 over x? We can write that as minus 2 times x to the minus 1. So when you differentiate, we apply the product rule. The minus 1 pulls into the front. So it's now a plus 2, and it's x to the minus 2. We could also write that as 1 over x squared, x to the minus 2, though it's not necessary here. So that's going to be the f prime. And next we multiply by g as it is without changing a thing. So this is 3x to the 9th plus 6 root x. Okay, so if we want to label the terms in our product rule, that is the f prime g. So what we're missing now is the plus g prime f. Let's get it. So the derivative of the g function with respect to x, it gives 3 times 9, which is 27. x to the power 8. Tricky business. Differentiating the plus 6 root x. So x square root is going to be x to the 1/2 power. We can use the power rule then. So pulling down the 1/2, it's 6 times 1/2 plus 3, and then x is now raised to the minus 1/2 power. In the power rule, after we pull down the exponent, we reduce the exponent by 1. So from 1/2 to minus 1/2. Okay, so that will be right there, the g prime, and we multiply by f exactly as it is. There's no reason to perform any algebraic simplifications. Actually, we're given license not to do that at the very beginning of this worksheet. We need not simplify, which sounds like old English, but clear enough, we don't need to simplify this. And we've solved yet another problem. Shall we keep on going? I'll hold the phone. Now, for longer problems, it's always advantageous after you finish a lengthy calculation to reread the directions. Why do we do that? Well, we easily get sidetracked. And by we, I mean me. So I easily get sidetracked in my own work. So if I have done a long calculation, I might have lost the thread somewhere along the lines and forgotten extra things that need to be done. Sure enough, I need to evaluate this derivative at x is equal to 1. So we can say, therefore, dy dx at x is equal to 1, and just super meticulously replacing all of the x's by 1. So the x to the minus 2 is now 1 over x squared, or 1 over 1 squared. So that term itself is going to be 1, but then there's a 2 factor in front. So it's going to be 9 plus 2, or 11. The next factor from that first term is going to be 3 plus 6, since replacing x by 1 gives us great simplification. So 1 to the 9 is 1, and the square root of 1 is 1. So it's times 3 plus 6, or 9. And then the next one, does our luck continue? Replacing x by 1 looks pretty nice. It's going to be 27 plus 3, so that is a 30. And finally, replacing x by 1, we get 9 minus 2, which is going to be 7. Okay, we can calculate this manually. I believe it's 99 plus 210, which, adding the 90 to the 210 gives 300, and there's a 9 spillover. So it's 309. Okay, let's go ahead and try the next problem. In the next problem, we're tasked with finding dy dx, and here we have a quotient of two functions. So we're going to have to make use of the quotient rule. We know that the quotient rule, it states that the derivative with respect to x of the quotient f over g, it's going to be f prime g minus g prime f, and all this over g squared. A good mnemonic for remembering this rule is it looks just like a version of the product rule in the numerator, but it's a twisted version where the plus symbol has been changed to a minus symbol. That's actually helpful to remember the quotient rule. If you can remember the product rule as being the derivative of f times g with respect to x is going to be f prime g plus g prime f. Quotient rule, just change that plus to a minus and remember to divide by g squared. Okay, so let's go ahead and label the top function f. So that right there is going to be the f function. We'll label the bottom function g, and we'll systematically apply the rule. It's going to be a little bit messy. Fortunately, we don't need to simplify in this worksheet. Make sure you here address your teacher if you don't know regarding your homeworks and your tests to get your solutions to be put into form that your teacher wants. So if they want to see Simplification, you need to know what type of simplification and how far to go. There's seemingly more and more work that can be done from these problems because our answers churned out by the product and quotient rules are pretty rough around the edges. So you want to ask your teacher to make sure that you're solving your homework problems and test problems, quiz problems, etc., to the specifications desired. Now, in this case, we have F and G as given. So I'm going to write the rule or just refer to it. We could put a big division bar for starters. How big to make it? So probably that will be large enough right there. And then in the denominator, we'll go ahead and just write G squared. So that is 7x squared plus 1 over x quantity squared. In the numerator, we do this funky version of the product rule, but with the plus symbol replaced by the minus symbol. So f prime is going to be 12 times 3, which is 36x squared, plus the derivative of 3x, times the g function, which is, as it is, 7x squared plus 1 over x. So that's the f prime g. Now a minus symbol. G prime is going to be 7 times 2, or 14, and that x is now raised to the power of just 1. The derivative of plus 1 over x, since that is x to the minus 1, is going to be minus x to the minus 2 by the power rule. And this is multiplied by f, which is 12x cubed plus 3x. And with that, we have written our derivative for that y function. Let's use a different color to do the next one. And we'll just move this slightly out of the way. In this next one, we're going to have to clear what is the f and g, because we're going to redefine f to be now this numerator. We'll define this denominator to be g. You don't really need to write clear FG in your work. That is an old habit from computer programming. When you want to reuse variables that already have definitions, you literally must clear the definitions, like in Fortran code, typing clear F or something of the sort. So that dates me when I talk about coding with Fortran. So here, let's get our derivative now. So we have dy dx equal to the derivative of the numerator. Let's first do the division bar. How about that? So that should be enough space, I think. And we have in the bottom g squared. So that's the easiest part to write, right? Not much thought, just cut and paste the g function and square it. Now the hard part, in the numerator, f prime. Well, we'll differentiate x to the 1/2 with the 10 out front, so it's 10 times 1/2, or 5. It doesn't look like a 5. Let's try again. 5 x to the power minus 1/2 minus 4. There we go. We got f prime times g, which is 6x cubed plus 3x. And because this is a quotient rule, make sure to use a minus symbol in the middle. And we have g prime times f. It's super helpful to have the formula right in front of you when you're writing out your derivatives. So the g prime, it is 18x squared plus 3. And that's multiplied just by the f function. And just like that, we have taken down another derivative problem. I'm not checking the work after the fact, but a good practice is, if you have the time to verify your calculations, you do that during the calculations, after the calculations, if you have the time to do so. I will not do that. So if there are typos, you can leave comments in the comment section. I am only human, so I am subject to the same blunders that all other humans doing mathematics can make. Even though I have a doctorate in mathematics, that doesn't exclude me or any other doctors for that matter from writing here blunders into their work, because we do lose concentration in the process of doing mathematics sometimes, and that's where those blunders creep in. Let's try number 5. So it reads, find the equation of the tangent line to the curve given at the point x is 0. It's helpful always to write a point slope form, provided that the tangent line is not vertical. This would be a good blueprint written in the blue color. Look at that, for the equation of the tangent line. Here, we're actually told that x1, the x value for the point of tangency, is 0. That means that y1 would be f of x1, which is f of 0. And we are clearing f and defining that function to be f. But because our workspace is small, I'm going to just go ahead and get rid of that. So we are defining this expression to be our f of x expression. And one thing that's missing here would be what to use for the m value. Recall that the derivative, it has a wonderful property that when it's defined, it returns slopes of tangent lines. Hence, the slope of our tangent line should be the derivative evaluated at the x1 value, which is f prime of 0. So this lays it out what needs to be done. We've already determined what to stick in for x1. So that's like 1/3 of the work needed, if you think about it, right? x1, we need to stick in the value 0. While we're at it, y1, that's f of 0. So put in 0 into the function, and you get in the top 1 and the bottom, you get 1 as well when you stick in x is 0 into that expression. So 1/1 is 1. And we're 2/3 of the way done. So now just what to put in for m. So let's do the calculation for m here. So we have m, it is f prime of x, evaluated when x is equal to 0. Aside, we have f prime of x is given by the quotient rule. So we have the derivative of the numerator function. If you want, you could call the numerator u, the denominator v. So I'm going to write u prime, which is just u the x, times v, which is x plus 1, minus v prime, which is 1, times u, which is e to the x. And all this is divided by, well, we can make that look nicer. So let's use the built-in shapes feature in OneNote. Isn't that pretty? A perfect line segment. So here, is it perfect? We'll never know. We divide by here what is v squared, which is going to be quantity x plus 1 squared. Now, this implies that m is equal to, we're going to evaluate f prime at x is 0, which is going to give us here 1 times 1. So it's 1 times 1. We're plugging in 0 for x, minus 1 times 1. And all this is divided by So wrapping up the calculation, we'll plug in x is 0 into f prime, and we get the result 1 times 1 minus 1 times 1. Oh, that's nice. It looks like the numerator is 0. In the denominator, when x is 0, well, it doesn't matter much, does it? We have 1. So rechecking, it looks like indeed we have 0. Our answer is just going to be y is equal to 1, okay? Now, as far as a check on the work graph of the function, you can see that when f is graphed in the xy plane, sure enough, at x is equal to 0, the tangent line does indeed appear to be going horizontal. And that is to be expected when we find that the tangent line has slope 0. So I can actually draw that tangent line right there. Let's draw it in a thinner line. So there is our horizontal tangent line. Y is equal to 1. So here we can see the tangent line indeed looks like it's just glancing the graph at the point 0, 1. Okay, so that is confirming the work we did. It's always nice to get some sort of graphical support to reinforce and not necessarily validate, but provide here at least a check to see if things go wrong. I mean, we could see visually if it wasn't looking like at all y equal to 1 was tangent to the graph at x is equal to 0. But in this case, there's support for our work from this visual display. Let's go ahead and continue on. In our last problem, we want to compute f double prime, and we can see that our function as given, it's a product. So we can call that factor u and this one v. And now applying the product rule to get f prime of x. So we're going to do f prime of x is u prime times v plus v prime times u. And so here the u prime is 6x squared, and that's multiplied by v. The v prime, that's an e to the x, and that's multiplied by u. Well, when we go for f double prime, we'll have to clear u and v and redefine them in each of these terms. So the new u will be 6x squared, the new v will be e to the x. Perhaps you can do this mentally in your head. Let's give it a shot. Derivative of the first function is 12x multiplied by the second function plus derivative of the second function multiplied by the first. Now that's just the derivative of the first term in f prime. So now we'll need to add, and we go around again. The derivative of the first function, this time being e to the x. So that's e to the x times the second function plus the derivative of the second function, which will be, in this case, 6x squared times e to the x. And we messed that up. Let's make this look pretty. Times e to the x. There may be like terms here. Standing back, I have a linear monomial term times e to the x. I have a quadratic monomial term times e to the x. I have a cubic monomial times e to the x, and then I have a quadratic times e to the x. So sure enough, these two are like terms, and they might even be the same term. So we can combine them. That implies that f double prime of x. Let's pull out the e to the x. And we'll write, we got 2x cubed. There is plus 12x squared and plus 12x. Of course, you could do more. You could pull out a 2 maybe. You could pull out an x if you wanted to, but that won't be done. We'll go ahead and stop here. We have a valid representation of f double prime, provided that there were no blunders. And with that, we've just finished another worksheet, this one on product rule and quotient rule. If you have any questions or comments, feel free to leave them in the comment section. And remember to click the like button if you like this video and share it if you think it'll help your friends and your classmates. I'm Dr. Mandelkern, and I am signing off. Bye-bye.